Again, good morning and welcome back to this lecture series. And today I'm actually going to introduce the nanomaterials and nanostructures. And today's lecture will be an introduction to that topic. And then I'll move on to these other areas that I have listed here. So this is the first lecture on nanomaterials. So it's an introduction. Obviously, the vision of nanomaterials and the technology that we're talking about was originally envisioned by the famous physicist Richard Feynman. You see a picture of him giving a physics lecture there. So here is a talk he gave that was titled "There is Plenty of Room at the Bottom." This was at a American Physical Society meeting at Caltech back in December of 1959. And he said a few remarkable things. The principle of physics, as far as I can see, do not speak against the possibility of planning things atom by atom. Planning things atom by atom. And he also further said the laws of physics do not limit our ability to manipulate single atoms and molecules. So you can see that all the statement really reflects on what we see in the nanomaterials world today. So, there's a lot of opportunities and challenges. So originally when this idea came into picture, there was a lot of hype. And hype came from titles like this: Economy of Promises, Can Nanotechnology Cure Cancer by 2015? And we are now already into 2023, and the cancer hasn't been cured by nanotechnology. So basically all this sort of came from popular media about this new technology. So, or is it reality? So, my view is that obviously this is reality, but we should not try to oversell, because there's a lot of scientific and technological challenges that we need to overcome to claim some of these claims that appeared in popular media. So as scientists, we have to think and we have to be realistic. So with that, let me show you some projection of market growth in nanotechnology. Some of the earlier data, you can see it has been divided into nanomaterials, nano tools, different color. So this is tools that we use to make nanomaterials or characterize nanomaterials, and then nano devices. And you can see most of the growth was predicted in the nanomaterials sector, and then overall growth in global nanotechnology market between 2021 and 2026 is about 12% growth. So it's a very, very robust area for materials development and research. There are all kinds of applications, and I'm just listing only a few. So-called nanomaterials related synthesis and manufacturing techniques. And there is a huge area of nanobio. Some of the materials that we are making would have their first uses in biological sciences. And then obviously the huge areas, nano-electro-opto technology or nano-electro-optics. So nanomaterials used in electronics and optics and so on. So these are some of the areas that people are looking for applications in this material. Size and scale wise, you know that nano is 1 billionth of a meter. And if we are dealing with few atoms and molecules, we're dealing with things at the angstrom level. when we are dealing with quantum chemistry and physics. When we deal with hundreds of thousands of particles, we are dealing with things in the length scale of 1 or 1 to 100 nanometer. This is really the nano world. And then when we go beyond, R's number of particles, then we're going to go to this macro scale, microns and higher, and that's where the solid-state physics is active. So looking at some of the realistic things that we see on a daily basis and compare the sizes. So if you go to very small scale, and this uses so-called top-down approaches, and you can see a few things in the small scale. I'm sorry. This is top-down is the largest scale. Sorry, I take it back. So what you see on the upper end is tens of millimeter, 1 millimeter, and then micron range, human hair, and so on. So these are sort of macro scale, kind of top-down type of approaches, engineering physics approaches. So you drill things, machine things at this length scale. Then if you go to really nanometer scale and sub-nanometer scale, angstrom and nanometer to tens to hundreds of nanometer, that's the really nano world. And this typically synthesis technique is the bottom-up approaches, chemistry and biology and so on. So you will hear about, usually you hear about top-down and bottom-up approaches, and that's what it says. So here are some of the nanoscale sizes of glucose. You can see angstrom level, insulin, few nanometer, to some of these molecules which are in the nano length scale. A lot of the bacteria and biological cells go a little bit higher in the nano world. So we already talked about this. Nano is a Greek word, really means dwarf, a dimensional measure of 1 billionth of a meter. And you can see how you can go compare this diameter of the Earth with the size of a football, soccer ball, with the size of something called C16 or fullerene. So here are the length scale. So this is in nanometer. So this is sub-nanometer nano world, and then bigger than thousands of nanometer and higher. You can see some of the real-life materials that we deal with, starting from biological material, biomaterials, to gold shell nano-structure, to quantum dots, to fullerene. So this is what we are dealing with in the real world, nanomaterials. One of the biggest advantages of nanomaterial is the enhancement of the surface area that are applicable to surface reaction-based technologies like sensors and catalysis and so on. So if you look at the large length scale, so if you make a cube of 1 centimeter side, the surface area, total surface area would be 6 centimeters squared. If you make the cube, same size material with cube made up out of 1 millimeter size cubes, then the surface area will increase 60 times. On the other hand, if you deal with the same size of the material, substance, fill it with 1 nanometer size cubes, you're actually making huge increase in surface area. So you can see really the dramatic increase in surface area. And if you do some simple calculation, if you go from macro scale to 1 nanometer size particles, you can actually take 10 grams of that nanoparticles. You can cover that equivalent surface area. You can cover a cricket stadium. Really, that's amazing of how much surface area you get we enhance by making materials at the nanometer scale. That's one of the biggest advantages. You can manipulate physical properties, for example. So here is an example of a cadmium selenide, zinc selenide core shell nanoparticles, size-dependent properties. So core cadmium selenide, zinc sulfide is the shell, and depending on the size, you can see that the color changes, that we are changing the band gap. So as you move from blue color to the red, you're making the band gap smaller and smaller. Here's another amazing things that you can do with nanometer scale materials that they can be self-assembled. If you take proper number of germanium atoms deposited onto a correct type of silicon surface. So if you take a single crystal silicon surface, a particular type surface, and deposit some germanium atoms on it, then the interaction of the atoms with each other causes pyramids to form spontaneously. It's actually, you see the top of the pyramids here. So they organize the germanium atoms and form something like this. You can see it's getting organized on the surface. This is the top of the pyramid. So this is what you're seeing in this view graph here, two-dimensional view graph. If you tilt and take a sort of three-dimensional view, that's top of the pyramid. And so it looks like a pyramid. So germanium atoms are being self-assembled into this pyramid. So this is an interesting self-assembly that I'll talk about. Here's the next important aspect of nano world that I want to highlight. So if you look at the number of atoms and compare that with one dimension, then in one dimension, the size will linearly scale with number of atoms and molecules. If you go to two dimension, the number of atoms contained in the size, or the relationship will be square of the number of atoms. If you go to three dimension, it will be proportional to n cubed. So the point I'm trying to make, you can see now that let's say if you take large size material, something like this, large scale, and you can see compared to the number of bulk atoms that just reside in the bulk of the material, the number of surface atoms are minuscule. So the property of the bulk material naturally will be controlled by the bulk atoms as opposed to the surface atoms. On the other hand, if you take materials at very small length scale, few nanometer, then you can see most of the atoms are sitting on the surface. While here, the bulk atoms are dominating the property, here, the surface atoms are dominating the property. So that means if I make a millimeter size copper, which is something like this, as opposed to 5 nanometer copper, most of my copper atoms in that 5 nanometer material will reside on the surface, as opposed to, and control the property, as opposed to millions of materials residing in the bulk with only a handful residing on the surface. So there is no reason to expect that these two pieces of copper will behave the same way. That's a very, very important concept for material scientists. So bulk versus surface properties. Surface properties, I show you some example. Bulk properties, surface properties are determined by atoms within a few angstrom of the surface. So in nanomaterials and nanotechnology, surface properties dominant over the bulk properties. If you take a dimension of 100 nanometer, the surface volume will represent 20% of the total volume. On the other hand, if you take the surface volume of 1 cubic centimeter particle, the surface volume is a tiny fraction of the total volume. So you can see that in this case, these can still be very dominating factor, but in this case, these do not play any dominating factor. So if you look at the nanometer scale gold, people look at microscopy, and within the resolution of this, it looks like we are making a spherical gold. Okay, but we know that gold makes face-centered cubic crystal if it is crystalline, and you can see gold atoms are sitting on the cube corners as well as 3 face-centered positions. If you take a cross-sectional view, you can see that these are the surface atoms, these are part of the corner atoms, and so on. Space-filling model. So this is the face-centered material. So how can nanoparticle of gold, if it is crystalline, be spherical? That's not quite possible. And so if you really think all this gold are crystalline, they should have this face-centered cubic type arrangement. So if as you move from the center outside, you will see some roughness, surface roughness. But so the atoms have to change position to make it spherical, smooth surface. It turns out that you can make material that is normally crystalline into an amorphous material, or even change the crystal structure entirely. So while a bulk material, bulk gold, would be face-centered cubic arrangement, a nanometer size gold or copper, you can see that the atoms, particularly near the surface, is not going to be arranged in an FCC crystalline manner. So they're going to be actually amorphous arrangement. So there is an effect in thermodynamics you may have heard, called Gibbs-Thompson effect. So this is melting point of, I believe it's the gold, and you can see that while the bulk gold melts at 1336 Kelvin, this is the melting temperature actually dropping substantially as you go to few nanometer level. So here you can see the melting point of nanometer scale can go down from 1336 Kelvin to something like 600-700 Kelvin, and that 600-700 Kelvin is a little bit above 300 degrees Celsius. So you can clearly see that the bulk material is behaving very differently than the nano size scale material. There is something called Moore's law that you all are familiar with, and it deals with how many transistors can you pack. How can you increase the packing density of transistor on a chip? And you can see a Moore's law prediction. At some point, it actually exceeded the Moore's law prediction. So where is the limit? So should we keep on packing high density devices, transistors, and so on onto small size? And is there any limit? Of course, there is a limit based on what we talked about. So when you are making material at the bulk level, and if you gradually decrease the size smaller and smaller, obviously that length scale is not simple reduction of the size. It's not a scale reduction of the size, but you can see that when you make materials at this length scale, most of your atoms will be residing on the surface, and the property can be dictated by those atoms, like the melting point of gold, things like that. So we should not be expecting that the transistor that we are making these days, and if we keep on making silicon-based transistor, let's say at the nanometer or sub-nanometer scale, we should not necessarily expect the same property. Okay, so not only there are technological issues that we have to think about, how to miniaturize, how to put contacts, how to get the signal out at that length scale, but we have to think about the physics and chemistry, fundamental physics and chemistry that can entirely change at that length scale. So we have to deal with the challenges of technology, as well as we have to deal with fundamental physics and chemistry at that length scale. So here is some report that was published back in 2017, new transistor concept based on metal nanoparticles. It's interesting, with energy gaps, metals with energy gaps. It says metal nanoparticles so small that they no longer show their metallic characteristic under current flow, but they do exhibit an energy gap. Okay, so this is interesting. You can see that making nanometer scale material can have completely unexpected properties. So if you're making materials 1 micron and larger, photolithography is a good technique to make the material that you can create feature size, and you can deposit material through those small feature size and make material which is roughly about 1 micron and higher, larger. You can use projection lithography to make sub-micrometer materials. So that's the limit. So how do we make materials of the nano length scale? So there are some techniques, exotic techniques. So for example, in this case, we use an AFM stylus, which is hard, and you can deform a soft material like a polymer, and you can create features simply by mechanical displacement, if you wish. So in this case, someone actually created Pablo Picasso's Don Quixote, curved on the surface of a polycarbonate film with an AFM tip. Or you can use a focused beam of photons or electrons or other energetic particles to induce change in a resist material, photoresistance. So you can see that you can deposit photoresist using photon beam or electron beam and cure the photoresist with the length scale of that beam, and then create features. University of Washington, written by E-beam lithography, very fancy techniques. Or you can use something like, you can take a piece of silicon and through, let's say, an AFM tip, you can apply electric field and locally oxidize silicon into silicon dioxide. So this white features that you see is oxidized silicon on a silicon substrate. So you can see that. So this is scanning probe. So this is an AFM image of scanning probe, probe that was used when you apply an electric field and oxidize silicon locally. So these are very fancy techniques to create nanostructures, and these are available under so-called nanotechnology or nanolithography. But these are like your microscopy, these are expensive equipment. So not only you have to invest a lot of money up front, capital investment, but also you have to hire someone to maintain these facilities. What I'm going to talk about is there are other non-expensive techniques, such as for making nanoparticles. There are wonderful sol gel, high energy ball milling, solvothermal techniques. So these are very well established techniques. And then there are techniques where you can create nanotube, nanowire, nanorod, nanobelt, etc. by using evaporation technique, laser ablation, where you ablate material and deposit in finer scales. So-called VS technique, vapor solid technique that I'll talk about. VLS, vapor liquid solid technique that I'll talk about. Anodization, I'll talk about. Metal oxide metal process that I'll talk about. Electrospinning, I'll talk about. Emulsion templating, photoelectrochemical etching that I'll talk about. And there are other surface modification type techniques that I'll talk about. So this is only a partial list of all this technique that's available that people are using. Okay, so starting with sol gel, you start with a sol that you can buy. Then, you buy metal alkoxide solution. So this is commercially available. And if you buy highly pure metal oxide solution, it's going to be expensive. So the expense will depend on the purity of the metal oxide. So that metal alkoxide will go through a hydrolysis and polymerization process. There's a lot of steps, chemical steps in this process that will create the sol. And then you can take that sol and precipitate out the solid particles, or you can go through a gelation process where you can get wet gel, and then you can extract the solvent and create this aerosol, or you can simply evaporate and let the particles collapse. That would be called zero-gel. And then you can heat treat and densify that material to make a dense ceramic. Or you can take your sol and make a coating on a substrate, and then you can do zero-gelling and eventually densifying and create a thin film. So there are various things you can use in the sol gel process. So the most obvious precursor for oxides are molecules have already metal oxygen bonds formed in the solution, such as the metal alkoxides. So this is what you buy as the precursor for making your material. So with respect to hydrolysis and polymerization process, you can see a lot of mechanistic approach going from gelation to eventually crystallization. So when you hydrolyze, so the polymer will go through some chemistry and orient and interact with each other. It will form a gel, viscous gel. We heat up, we can make nanoparticles, spread those, and make thin film. Okay? So there's a lot of heterogeneous nucleation, a lot of nucleation and growth process, and even phase transformation happening during this hydrolysis and polymerization process. Pyrolysis is a thermochemical decomposition of organic material, the pyrolysis process. And you can actually control the speed of the pyrolysis process, make it slow, make larger particles, or you can make the pyrolysis process faster and make smaller size particles. You can add so-called chelating agents to control the speed of the pyrolysis process. Anyway, if you're making, for example, titanium oxide, so you can use titanium precursor. So these are all titanium precursors that are commercially available in making tin dioxide. So you can see these are the precursors that you can buy. And use solvent, various alcohol as the solvent, and complexing or chelating agents. I talked about to speed up the pyrolysis process or slow down the pyrolysis process to control the particle size. And then the crystallization is done in this temperature range depending on the material. When you're initially making amorphous material, then this high temperature treatment make it crystalline particles. So here are some sol-gel silica, very uniform size, submicron size, the sol-gel tin dioxide nanoparticles. So you can see the individual particles are going to be tens of nanometers. You can make actually compound, multi-pattern materials, something like barium titanate. Again, nano-sized particles. You'll obviously have to use two metallic sources, sources of barium and sources of titanium, to precursor, and goes through various processes. Eventually, you dry calcite and crystalline the powder at high temperature. So you can make single cation oxide or multi-cation oxide, refluxing it just like heating the solution without allowing the solvent to evaporate. This is done by using a reflux condenser, which condenses the solvent evaporating from the solution being heated. So we do it under high pressure where solution does not evaporate. So some general aspect of the sol-gel process, very versatile. You can make powders, films, fibers, monoliths, aerosols, aerosols. High purity, you can control it by the purity of the starting alkoxide solution. It can give you homogeneity, limited mass scale. You cannot produce tons of materials. You produce only a handful. You are dealing with application that requires a few microgram of particles or thin coating or thin film. And sol-gel is really a wonderful technique to make nanomaterials. Moving on to VLS, vapor liquid solid technique, where you actually, so if you're making silicon nanofiber, for example, on a silicon substrate, you can actually first put dispersed iron particles on the silicon substrate, and then you supply your siloxane gas, silicon tetrahydride, as the source of silicon, and that gas will be carried by an inert gas. And then it will come in contact with that iron that forms eutectic melt at the heat treatment temperature. And from the binary phase diagram, you can see it makes an eutectic melt. So this gets absorbed on top of that eutectic melt, dissociate into silicon and hydrogen, and the silicon then dissolved into that molten eutectic supersaturates and it starts precipitating at this interface. And then as you keep supplying this source gas, it will actually, the process will continue with silicon growing as a rod with that eutectic melt at the tip. And you can see after you're done, one of the characteristics of silicon nanowire will be able to identify that eutectic melt. So that's an indication that one has used a VLS technique. And you can see the mechanism, mass transport in the gas phase, then condensation onto that gas liquid interface, diffusion into the liquid phase, dissolving, and crystal growth at the liquid crystal interface right there. You see the detail of what I talked about. Moving on to the next topic, which is the VS, vapor solid, no liquid involved. So in this case, what you're doing, you are simply taking a substrate and you're putting that substrate at a lower temperature than compared to the high temperature source zone. So again, you are sending the siloxane gas from high temperature region, and your substrate is placed at a lower temperature. So your gas molecules start condensing on that colder substrate, and then it just grows one-dimensional nanobelt or nanotube or things like that. So the question is, what is confining this one-dimensional feature? Why not form a uniform thin film on that substrate? So there's a lot of issues about there must be some nucleating agents that the rod or nanotube nucleates at some preferred location, and then it keeps adding to that instead of nucleating at other locations is not equally filled. What is that nucleating? In some material, it could be screw dislocation, for example, or some sort of defect, sort of stacking fault, or so this is not completely understood, but people do use VS mechanism to make a lot of oxides, for example. Oxides, particularly the oxide that can create high vapor pressure at high temperature. So for example, you can grow nanotube of tin dioxide material by first packing tin dioxide powder in a hard zone. And what you're going to do is heat it up, and you create tin monoxide vapor, and then that vapor is carried by inert gas like argon, and the gaseous species will condense onto this low temperature substrate. And you can see, some of the condition for growth. And then that's how you deposit, and here's some microstructure materials grown by VS, and you can see you're growing one-dimensional structure, and you can confirm by what material you are growing, both the direction as well as the interplanar distance will give you the crystallinity of the material. So typical widths of the nanobelts are in this range. You can see still in the nanometer range. The length can be several micron, rectangular shape cross section, so it's a nanobelt in that sense. And people have made nanobelts of all these materials. You can amazingly see that titanium dioxide is missing. Can you guess why? Well, the reason titanium dioxide is missing is one of these material. This is one of the oxide where you cannot create any high vapor pressure phase. The thermodynamics, you can look up thermodynamics, and indeed in reality, well, you get very high vapor pressure of all of this oxide, not for TiO2. The electrospinning, so you can create nanoware, for example, by electrospinning. A polymer solution or mold is injected in this plastic syringe, and then you force the material to come through a fine nozzle under the influence of an electric field. So you apply a high voltage between the source and the substrate, the collector. And that can be a controlling parameter. The buildup of electrostatic charges on the surface of the liquid droplets coming out as droplets can be less static force on that liquid droplet surface, induces the formation of continuous ultra-thin fiber. And that's what you're depositing onto the substrate. So people have made different types of material, various engineering plastics, biopolymers, electrically conductive polymers, electronic polymers, and oxide nanowires, and so on. And the controlling variables of the electric field strength, tens of kilovolt. And you can add different molecular weights, different size of molecular weight, and you can control the deposition distance as well. So here are some examples. So this is the TiO2 with EVP polymer composite. So the green state before firing. So this was deposited by electrospinning. And after you fire at 500 degrees C, you can see the polycrystalline nature. So you're actually burning off organics and so on, and volatiles, and you come up with this polycrystalline TiO2 in this case. And this is the precursor that was used in making the solution, and the polymer that was used. And then eventually you burn off the polymer and make a polycrystalline material. You can actually make a hollow tube, TiO2 hollow tube, by doing this by forcing. So while you are depositing the nanofiber or nanowire of your TiO2, you can actually flow a heavy mineral through the pore of the fiber. So this is a coaxial jet. So you're going to make a coaxial material. One will make TiO2 fiber, and the core will be the heavy mineral that you can etch in octane and etch out that heavy mineral oil and make hollow nanotube. You can see the hollow nanotube and the larger scale hollow nanotube. Looks pretty regular shape, very amazing type of material. Here's the other technique called anodization, very popular technique, where you have to use you're actually doing etching, oxidation and etching simultaneously under the application of electric field. So if you're trying to make TiO2 nanotube, for example, you start with a titanium metal foil or something like that, and you put it in a solution, electrolyte, in this case, 0.5% hydrofluoric solution. That's your electrolyte that will supply oxygen for your oxidation, and then you apply an electric field. So put one electrode on the back of the titanium substrate and insert the other electrode into the liquid electrolyte. And you supply voltage of this order of magnitude, and you're going to do oxidation, where oxygen comes from the electrolyte of the titanium, and then dissolution at the same time. So you're going to form the oxide, dissolve certain part of the oxide, so you create a hollow tube. So it's a field enhanced oxidation dissolution process. And you can see that you're growing thin film of oxide that is getting etched. And as you create the etching site, then electric field is highly concentrated in the valley here, right? And the drilling of the etching becomes anisotropic. So it will be etching more and more material from the tip of the hole than from this part of the oxide. So you can eventually see that it's anisotropic drilling. So you're basically going to create this hole and keep this material as in between the hole, basically. So you can do a similar process to create anodized aluminum oxide with holes that you can buy commercially. You'll be starting with a piece of aluminum and going through an oxidation and dissolution process. So if you look at the chemistry, obviously the oxidation is driven by the source of oxygen and the electrolyte. So you can see the water molecule dissociates into oxygen and proton, and your titanium will react with oxygen forming TiO2. And then the titanium 4+ ion will react with the fluoride ions and make this titanium oxyfluoride ion that is dissolvable. So this is a dissolvable product. You can see TiO2 reacting with fluorine ion and the proton and making this complex that is dissolvable. So with that, you can see the structure of this titanium nanotube. So, through the top of the nanotube, and is a three-dimensional view. So you can see nanotube actually has certain length, and it will depend on the time. So here are some dimensions of the nanotube. As received nanotube is typically amorphous and oxygen deficient. So it will require post processing annealing, so that you can convert the amorphous into crystalline and also make up for the deficiency of oxygen. So the next process I'm going to talk about is bond metal oxide metal. So you start with an anodized aluminum and a hollow tube. Okay, so one side of the tube you actually plug it with silver deposited by electroplating. And I've given you condition of electroplating of silver and gold and tin and nickel and so on. So what you do is put electroplated silver here and plug one side of the tube. And then you electroplate gold. So on top of that silver, you grow gold into each of this hollow tube. And then if you're making, let's say, tin oxide, then you electrodeposit tin. If you're making nickel oxide, you electrodeposit nickel. And then you electrodeposit gold again. And then you have to use dissolution agents. So you can dissolve silver in this solution, silver, and then you can dissolve the alumina, anodized aluminum, in this solution. So you end up with this gold, nickel, gold, or gold, tin, gold type devices. Now, if you want to convert this tin or nickel into oxide, just do oxidation in the air. You convert this into oxide, there will be some volume change, so there may be some micro cracks at the gold, tin dioxide, or nickel oxide interface. Okay? So if you make this very small length scale, the micro cracks will not be as severe. So now you can see basically you have a device, an oxide connected with two metals that you can measure signal. And this is metal oxide metal, so-called MOM process that you can use. Finally, I'm going to talk about a technique that I learned about my visiting professor Minoura's lab at Gifu University in Japan. He's actually taking polycrystalline sintered TiO2, titanium dioxide. So that's a piece of TiO2, sintered TiO2. You can see sintered TiO2. And then he puts in a solution, sulfuric acid solution, and apply electric field to connect one electrode with the sample, the other electrode inserted in the solution. And then shine with UV light. So this is, you're going to create, and eventually you create this kind of nano honeycomb type structure. So these are the single grain TiO2 that has been etched to create this rectangular shaped nano holes. So this is an electrochemical etching, that is electric field electro, chemical from the chemistry of the solution, electrochemical etching. And there's UV light. So what the UV light is doing, UV light is focusing onto the TiO2 sample, and it's creating this electron hole pair by exciting electron across the band gap. And since the band gap is above 3 electron volt, you have to use UV light. So it creates the electron hole pair. And then you will see that you will need this hole to create this dissolvable titanium sulfate complex that can be dissolved, which is giving you this etching property that creates the hole. So it's titanium oxide on the surface, reacts with the sulfate ion from the solution, and it uses this hole, electron hole that you created, and it forms this dissolvable complex that is dissolving. So this is the very interesting process. Why is it interesting? Now you can see by creating this nanometer scale holes, you've increased the surface area of this TiO2 grain tremendously. Your gas can percolate through, interact on the surface, and give you sensing, for example. So this is really an interesting process. So you can see this is an area where you can do typical material science. You can change the processing parameter. Then you can go through characterization and property measurement, and you can go back, change the processing parameter to change the microstructure and crystal structure of the material to see the enhanced, its impact on the performance. And this is really a potent area to material science. With that, I'm going to conclude this lecture, and then in the next lecture, I'll move on to surface modification technique to create nanostructures.